Okay, so good evening, everyone. Thank you for coming. So today we'll have Cheng-Li from Princeton Physics. Cheng-Li is currently a PhD student at Princeton University in Ali Yasdani's group, and then he was from Taiwan, and he finished his undergrad at National Taiwan University, and his current research interest is using scanning turning microscope STM to study 2D materials, especially like graphene heterostructure. And then the reason I kind of know Cheng-Li just we back to Taiwan, we were kind of a colleague, and then we also graduated from the same place. So kind of use this opportunity to invite him to come here. Yeah. So anyway, so please take it away, Cheng-Li. Thanks so much.
Yeah, thank you for the introduction. So today I would like to talk about some 2D material, like about my recent research, and I will also introduce about myself, my hometown, since there are so many Taiwanese people here. So it's good to introduce our hometown to the other people. Yeah, so just a brief introduction of myself. I'm from Taiwan, and when I'm in Taiwan, I like to biking. I used to ride road bike, and the good point of road bike is it's not too fast, so you don't miss the scenic, like beautiful view, but it's also fast enough so you can travel, go to a lot of good places in one day. So those pictures is in the central part of Taiwan where there's a lot of mountain, and so I ride like from almost sea level to you can see it's almost 3,000-meter high, like in about 8 hours or 9 hours. And the beautiful part is that you can see a lot of different terrain. You can almost like from the sea and then go to some little hill and then go to a really high elevation, and there you feel the oxygen level is really low, so it's struggling to like keep moving on those places. And I think the reason I do STMI also related to this kind of personality. I like biking, and actually 99% of the time when you're riding bike is it's actually pretty pretty tiring, pretty struggling, and sometimes more like self-torturing. So especially riding uphill, you actually have to push yourself pretty hard not to stop and even fell off, because sometimes the road is just very steep, and you have to use a lot of strength to keep your bike keep moving. But I think this kind of personality kind of helped me to do STM, because as I will mention later about doing STM is also involving a lot of hard working and something. I'm sure all kind of different experiments are also very hard, but I think this kind of personality helped me to do this kind of experiment. And when I'm here in America, moving from a tropical area, now I move to America. One thing I really like here is that it snows sometimes, so you can actually go to some resort to having fun with some snow. So I'm starting to learn how to snowboarding. I don't have too many pictures to put here, but this is a Blue Mountain Resort, which is 2 hours drive away from New Jersey, which is you can go there in one day, which is pretty nice. And I'm learning how snowboarding, and well, this is not me, but I definitely fail very often when I'm learning snowboarding. And I think doing 2D material research is sometimes pretty similar to learning how to snowboarding, because sometimes you really have to try, but when you try, you fail, and you even though you physically didn't feel the pain, but mentally it's really painful to try and failing and all the time just going to waste. But yeah, I think there's some similarity between snowboarding and doing research. Sometimes you really need to try, even though you know you will fail. But before you fail, you don't even know, you wouldn't know where you would fail. So you really need to get into it and like getting some bruises to be able to run in something. So yeah, that's about me. And I'm coming from Taiwan. So yeah, I was planning to play some video about country, but yeah, maybe we can do it later if we have more time. But Taiwan is a beautiful place, as I mentioned. I think the beautiful part is now we have some really big valley or some very big beach or mountain, but because we are small, so you can go to each of the like different places like in a very short period of time. You can like stay on the sea, like seashore in the morning, and then just go to like 3,000-meter mountain in the afternoon. And in the night, you can go to the city and having some food in the night market. So yeah, it's pretty good places. I'm really welcome everybody to come to Taiwan and well, maybe after coronavirus, of course, but yeah, it's a good place. You should definitely come and visit. So today I will tell, this is the outline I will try to cover today. So I'm using STM to study 2D material. So why doing 2D? So I will introducing about why 2D. And then graphene is one of the best 2D material currently people are doing research on. So I will introduce about graphene, this material. And then recently people must know about the twisted bilayer graphene. This is a very wonderful system, and people like study graphene for like almost 10 years, more than 10 years. But now with a twist, like everything seems to be like different, and a lot of interesting fixes coming out. And then I will introduce about the scanning tunneling microscope, which I'm using to study the 2D material. And then I will introduce how we fabricate our sample. And then in the end, I will try to cover two projects that I am involved in. And I will try to talk about the magic angle twisted bilayer graphene and the twisted double bilayer graphene. So, and if you have any questions, feel free to just interrupt me and raising your question. And
yeah, I have a question.
Oh, sure.
So are you still biking now? And
yeah, I didn't. I don't bring my bike here, and I actually like to bike the mountain more than like flat land, and I feel like New Jersey is too many flat lands. So I start biking now.
I see.
But maybe sometime I will try to buy a bike when I got enough money and pick up the habit again.
Yeah.
Do you bike?
Yeah, we both. I sometimes bike with my wife. Yeah.
Yeah. Okay. Maybe I can join you in the future.
Definitely.
Okay. So let's begin. The first part is I will try to introduce about the 2D. 2D is really like another world. We can think about like an ants working in like a maze, and you know, if for we who human more like live in a 3D world, when we're looking at the ant working in a 2D maze, what we see is very different from what the ant see. The ant, when it hit a wall, well, that means there's no way for it. It has to go back or like finding another way. And when the ant is in the maze, it doesn't know like how to get to the exit. And for us, for women, human, we can like look from the top. We can see how the maze is, and we can find the best route to the exit. So what I want to say is the electron in 2D and in 3D is also very different. When the electron is in 2D, many physics behavior would become like totally different than 3D. Something would be even more interesting in 3D. So for example, the very first physics question people might run is about the free electron gas. And we know the free electron gas, the energy of an electron is proportional to the k square. And you know, we almost learned this in the quantum mechanics, that we can calculate the density of state in the 3D system. But in the 2D, the behavior is totally different. Since now in a 2D, we only have 2k axes. So if we do the same calculation, the 2D material will give us more like a step-like density of state, which means if you in a 3D, it's more like a continuous thing, but for a 2D system, when you enter in a free Fermi like gas, you will see a sudden jump in density of state. And this, and in 1D, there will be even more different thing. There will have like a anomaly in the density of state. So electron can definitely behave very different in the system. Free electron gas is like the first thing we will notice. So another thing that is also very different is once we apply a magnetic field, the behavior of the electron gas will become very different. So the classical Hall effect, I believe people must know, is that the density, the resistance of like parallel to the current direction should be related to the material itself. So if you are using a Joule model, it depends on your realization time and the electron mass. And for the Rxy, the whole resistance, it should be proportional to magnetic field and the density. And we know that you can use in Hall effect to calculate the carrier density and the carrier type. However, this is a classical behavior when so this behavior doesn't matter when you are in 2D or 3D system. But in a quantum version, when your material get into really real 2D regime, there'll be a really interesting behavior. And if you write down Hamiltonian, the magnetic field would be appearing in the y momentum direction. And this will give us a very interesting result. If you transform it, like rewriting some parameter, you will find the Hamiltonian behave like a free electron moving in X direction, but in Y direction, it become like a harmonic oscillator. And your density of state and would totally collect to a single line, and you will have a lot of density of state degenerate into a single energy level. And the energy can be described by this formula where you have like a fixed energy separation, and this is depending on your magnetic field. So you see that in a 2D, this behavior only happen in 2D. If you're in a finite thickness, this lambda level will broaden up, and then eventually your quantum Hall effect will disappear. And this is very important result because, well, people get Nobel Prize because of this. And so this guy got a Nobel Prize because he realized this quantum Hall in the gallium arsenide. And to understand in this figure, we can think of a naive picture, which when you apply a magnetic field, the electron, because of the magnetic field, you will move in like a cyclotron behavior, and depends on your field magnitude of your magnetic field, the size of the synchrotron will become different, and that size would more like a lattice size, and in your sample with like finite size, you can use in this way to calculate how much density to fill one lambda level. And then from there, if you fully fill your lambda level, you will see that the whole material become fully filled. And in that cases, you will see a resistance resistance heating, well, you will see resistance change in R-axis and R-XY. When you are fully filled, you will see like a change in like a how to say, a discrete drum, and this drum can relate it to it has a h bar over e, like e squared, this kind of quantized resistance. And this is a very interesting behavior, because in the traditional quantum Hall effect, you are expecting the resistance is proportional to the magnetic field. However, in this diagram, you can see it has a lot of discrete jump. And something that's even more interesting is about some fractional statistic. In 3D, well, depends on the phase trend. When you exchange a particle, the particle can become a boson if you exchange it, it will give you a +1 phase trend, which is no change in the phase. Or it can be a fermion if you exchange it and getting a -1 phase. But so the phase I'm talking about is if you exchange in the position of two particles, you get this exponential I alpha pi, this term. And if this term is +1, we know it's fermion, and if it is -1, it is boson. And we know it depends on the, we know that it's always true in the 3D. However, in 2D, the phase can be actually any number. It doesn't have to be +1, or it doesn't have to be -1. And the reason behind this is because if we think about the exchange behavior, if we want to change in the position, you can think of if you're sitting on, let's say, for example, if you are on the A particle, if you want to exchange in it, you can think of the B going around the A and going to the other part, other side of the A. If you want to change it back, you just keep rotating it and going back to B. So you can think of the exchanging behavior. It's like the B circulating the A particle again. And when exchanging it, you move 180 degrees. And if you want to change it back, you rotate 360 degrees. So the phase pickup when you go 180 degrees is exponential I alpha pi. If you go 360, it becomes exponential I 2 alpha pi. And in 3D, because you have 3-dimensional, you can move in this loop out of plane, like the dashed line, and eventually can shrink in this loop and then making it basically disappear. That means if you rotate in a B again, you can continuously changing it to the situation where you actually didn't move your B particle at all. That means your phase when going 360 degrees should be +1. And so because exponential I 2 alpha pi is +1, your exponential I alpha pi must be +1 or -1. However, in 2D, you doesn't have this outer plane movement. You have to go around the A. So there's no way you can reduce in this loop to a single point. So that means if you go, if you want to shrink this loop, at some point you must touch in the A. And when you touch in the A, you will gaining some interaction, and your phase, this phase will not become +1, and you will have, it can pick up with whatever phase. It can pick up any phase that is possible. So you don't have to be +1 if you exchange a particle, or it doesn't have to be -1. So you can actually get some fractional statistic. And this will give, well,
sorry. Does it,
yeah.
Does it mean that in 2D, we do not expect boson?
So of course, most of the time it is a boson or a fermion, and in electron, it is a fermion most of the time. But it can be it can be other thing, which we will call it an anion. So it can pick up like 1/3, like 2/5, this kind of thing.
Sorry, I mean,
so
I mean,
yeah.
in 2D.
Yeah.
Because this, along with this argument, that seems to be indicating that in 2D, there will be no possibility that boson can exist. Is it the case, or I misunderstood somewhere?
So you know, most of the time it's still fermion or boson.
In 2D.
Yeah, in 2D. So that's a good question. Most of the time, the electron want to behave like a fermion, but it doesn't have to actually.
Okay.
And
this is my first time learning this explanation, so I'm pretty curious.
Yeah. Yeah, I'm an experimental guy, so pardon me that if I didn't answer your question. But yeah, it does behave like a fractional statistic, and this is give rise to the fractional quantum Hall, which also have a Nobel Prize given to this effect. So in the previous integer quantum Hall effect, you will see the spike, the resistance Rxs and Rxy jumping only at the integer filling, but in fractional quantum Hall, you suddenly see a lot more peak. The integer should be this one, and in the between, there's suddenly a lot of like different spike. And this is actually because of this effect. And if you remember when I'm trying to explain in the integer quantum Hall, let me go back to that slide. I'm trying to explain it by like filling your sample with a lot of electron cyclotron, and each electron basically absorbing one magnetic flux. And that is when in the integer effect. But when your electron become anion, which means it doesn't follow fermion or boson statistic, you will have a extra phase in front, and that phase it can be effectively explaining as a fermion carrying or boson carrying extra magnetic flux. So that means your anion is like a normal electron carrying a flux. So when you are in this kind of picture, in the beginning, you have one electron absorbing one magnetic flux, but now each electron already carrying some magnetic flux, so the magnetic flux can cancel the original magnetic flux, so making each electron actually absorbing more magnetic flux. So that's the reason why you can have the integer quantum Hall behavior happening at the fractional filling. So when your electron is carrying two flux, you will see like 1/3 or 2/3, and if you're carrying two flux, yeah, but like there's some conversion. I couldn't remember the formula right now, but yeah, depends on how many flux you carry. You can have in different type of fractional quantum Hall gap. So that's amazing that in 2D material you can have so many different behavior. So in previous experiment, it's mostly done in gallium arsenide. This kind of material, it's a semiconductor, and when you want to put in more electron in, it becomes very hard because it's if you want to gate in it, you need to grow in some very complicated heterostructure. So most of the time, the way they are changing the density is just sweeping the magnetic field and changing the cyclotron size. So your electron will fill in differently. But there's another new material, which is graphene, that's been discovered in 2004. That is very amazingly easy to change in the Fermi level. So this is graphene. People must know that it has a triangular lattice side, and in each unit cell you have two lattice points. So and each lattice point is made by carbon, and they have the covalent bond to bonding each other. And the Brouillon zone will become like a hexagonal lattice side. And this material is pretty interesting because if you calculate the band structure using a tie binding model, you will get a Dirac cone at the K boundary. You can think of this like, you know, in the free electron, when we calculate the band structure, it has a parabolic dispersion. But in the graphene, when you calculate it, the dispersion become linear. This kind of linear behavior is more like a photon, that kind of material. So sometimes we call this a massless fermion in graphene. And this material is amazingly easy to get, actually. And this is the original paper that helped the people get a Nobel Prize. And they successfully exfoliated the graphene. So we know graphene has, if you stack in a lot of graphene together, it becomes a graphite. And people has been using graphite like for, I don't know, 1,000 years because it's just your pencil. And however, like getting only a single layer of graphene from the graphite is something that people never think possible. And however, the people found that, oh, it's actually easier than they think. You just need to take a tape and put a graphite in between, and when you split the tape, the graphite become two. And then if you keep doing this, you can thin down your graphite, and eventually it can become like a monolayer stuff. And if you put it down on the silicon oxide, sometimes it will be dropped, and then you got like a monolayer of graphene and deposit on your silicon oxide wafer. And then you can, well, fabricating it and making all kinds of devices. And this is really a nice 1D material, a 2D material, because it's only have one atomic layer. It doesn't have finite thickness to affect in our quantum Hall effect. And also you can gate in it because you have a dielectric. And if you apply some voltage on your below material, which is silicon, you can dope in it, and then you can move in your chemical potential from the Dirac cone to other location, and you can change in the electron behavior significantly. So for example, in this this figure, the X is a gate voltage. So just like we are gating our CMOS, our like transistor, if you gate your your graphene, you can change in the resistance dramatically when you are in the Dirac cone, where there's very little electron sitting inside this energy level. You have a large resistance, and if you gate it away, you will see a resistance drop. And this turns out to be very easy to get. So people has been trying to improve in the quality from this, and when you can make the quality even better, you see the integer quantum Hall effect as well. And the behavior is somewhat different than the gallium arsenide situation, because graphene have some other degree of freedom. So you have spin, and you have different value. For example, you have K and K prime value. So it turns out you can have 4 degeneracy in each lambda level. And it happens that when you are at the Dirac point, it's already have like a quantum, like a jump in your whole resistance. So it's really a new platform that give a lot of phenomenal behavior. But all these are like the history, and what's happening happening in the field now is that when you having a graphene and then stacking them with an angle, you can actually get many different new fixes from it. So before that, let me introduce about the Moiré pattern. Some of you must be very familiar with this. Moiré pattern is actually just a mathematical thing. If you, well, I probably used the wrong one, but well, if you, okay, this is probably not wrong, but anyway, forget about this. If you add into periodic sine wave together, you can get a beating. This is something we learned in the fundamental physics. And this is in 1D case. If you're in 2D case, if you add in two sine wave or periodic thing, you see that you can easily get the pattern. The reason you see a Moiré pattern in this photo is because your camera is also pixel wise. You have a lot of pixel in your sensor. And when you are taking a photo on your monitor, the monitor is also made by a lot of little pixel. And the pixel of your camera and the pixel of your monitor have different periodicity. So when you're taking a photo of your monitor, you can get in this kind of beating behavior. And that's the reason why you see this kind of stripe in the monitor. So the moral of this is that if you put in two different periodicity together, you can get a larger, like a beating behavior, a larger periodicity in your material. And we know that periodicity is really the core of the condensed matter. If you've got a periodicity, you can change in your lattice. You can create a band structure. You can create some open a gap from, if you like add in some periodicity in your free fermion, you can open in a gap and creating some like band structure. And if you have more complicated periodicity, then you create a crystal, like all the topological and all the condensed matter fixes. So, but what's new about graphene with this kind of periodicity? So let's beginning with without the periodicity. If you have a monolayer graphene and sitting on top of boron nitride is also another 2D material. It has a different periodicity in monolayer graphene, but it is an insulator. So it's more like a substrate that you can put your monolayer graphene onto. And if you didn't align it, the Moiré periodicity will become very small to disappear. So you can basically consider it this kind of situation as no interaction at all. So you are just a normal monolayer graphene. And if you don't apply a magnetic field, you will have a Dirac cone, as I showed before. But when you turn on the magnetic field, it will become a quantum Hall. You will have a quantum Hall effect, and you will forming up some lambda level, and you can see that in the energy, you can in the density of state, you will see like a lot of state degenerate and like being collected on a single energy level. So as I mentioned before, you can understanding this as the magnetic field create a new type of lattice side, a new kind of periodicity, and then create a new type of like a electron C, and then this electron has the same energy, and they being collected on the single energy. So now you got using magnetic field, you can create one periodicity. What about you create another periodicity using the Moiré pattern? So now if I align the boron nitride and the monolayer graphene, from this image, you can see that there's like a larger periodicity. If you can, if you get what I see, there's actually like a larger periodicity on top of monolayer graphene and the boron nitride. And this extra periodicity can interfere with the original magnetic field form. It can interact with the previous periodicity. When you get this two type of periodicity, you can think of you are creating another band folding. We know that if you have created a periodicity, you can make in like a free electron gas into this kind of band structure. You open up a gap at the edge and then create like a folding effect. So if you fold in your original quantum Hall effect, if you fold in your original lambda level, you will get a very interesting behavior. And this thing look like a butterfly. I don't know, the previous people think that it looks like a butterfly. So they naming this as a like graphene Hofstadter butterfly. So this thing create like a new field for people to study how the graphene behavior under magnetic field with this Moiré pattern. But this kind of to create a Moiré pattern, another way you can just by stacking two graphene together, you will also create a Moiré pattern. So also you can, if you step back, you can see that there's like a larger periodicity on top of the original like graphene periodicity. So the similar thing can happen to this type of system. You add in an additional periodicity onto your original Dirac cone. What's going to happen is that you will basically cutting your Dirac cone into many little pieces and then opening up a gap at the boundary. So if you plot the densities of state versus the energy, you find that there will be a band being isolated, or you can say it's like being cut by bending your band structure, and you get a high density of state being collected near the Fermi level. And we know that in the, like for example, in the BCS theory, in order to get a higher TC, you need to get a higher density of state. And the same thing can like the same behavior can happen in other kind of quantum behavior when you have a large density of state have a large density of state around the Fermi level. The electron will getting very close to each other, and they will interact very strongly, and then create a lot of non-single particle behavior. For example, you can create some symmetry breaking, this kind of strongly correlation effect. So with this kind of proposal, people doing research on it, and people must know about this work if you are in condensed matter physics. So in MIT, they figure out how to make a measure angle twisted bilayer graphene. When you twist your graphene to a measure angle and you create a perfect Moiré pattern, you will get your flat band very, very flat, that the interaction can be so strong that creates some extra behavior. So if you remember in the monolayer graphene, you only have a Dirac cone feature. When you gate in the sample to a Dirac cone, you have a high density of state, but that's it. You don't get anything outside of that. But because of the Moiré pattern, you create a band folding effect, and you isolate a flat band and create a gap like between this flat band and some remote band. So let's create a gap, and you see it here. But on top of that, you also see some other insulating state beside it. You know, there's and it's supposed to be like a lot of density of state collecting together, but so it shouldn't have any insulating state when you only half fill them. However, it created one. So this indicating that there must be some new behavior happening. And that's not the most interesting part. The most interesting part is that they found a superconductivity beside the half-filling insulating state. And this reminds people about the high TC in high TC behavior, because in high TC, they also have the superconductivity dome around the mud insulating phase. You know, if people can figure out the mechanism of high TC, maybe they can push the TC to even higher and then like save the world basically. So this become very interesting topic, because you know graphene doesn't superconducting. However, by twisting two graphene, you create a superconductor, which is like something really new. So this sparked a very like a lot of people just jumping into this field, and people are also thinking about what if you are making another type of twist system. For example, if you have 3 layers and with some twisting, and how about twisting monolayer, bilayer? How about twisting two like bilayer graphene? Or how about making like 3-layer and twist it with a like twisting like with twisting angle? So I just put some like more famous paper here, but actually there's even more paper about this kind of twist system. So our lab is interested in this field as well. So we try to build a, we have a microscope, but we try to use in this microscope to study this type of material. So just a brief introduction. I guess I don't have too much time, but let me just briefly go through it. So you have the tip that can be very close to the sample surface. And when you are very close to the surface, you can get a tunneling effect. And you can describe in this type of tunneling effect using some Fermi-Golden rule. And when your tip is almost a perfect metal, and what you will get in the tunneling current is basically proportional to the density of state and the integration of the density of state and between the basically the Fermi level difference will have give you a region, and the area of your density of state between these two lines will give you the tunneling current. So using this tunneling current, you can basically measuring how much density of state is in your sample. And that's not the most interesting part of STM. The most interesting part is that you can scan your surface. So you can also detect in the density of state in real space. For example, this is a copper surface. And on the copper surface, you can see some defect, which is some like carbon monoxides, like from the chamber that's sitting on, been absorbed by the copper surface. And this defect can give you some when your electron hitting a defect, it will deflect and you will create some interference effect. And this will give in, we call it as a quasi-particle interference pattern. And using an STM, you can see those interference pattern because we can see the local density of state in real space. So using STM, you can see this kind of feature. So this is our system. We have a UHV chamber here. And because we are scanning the atom, so we need to lower our vibration as much as possible. So we have basically a floating room. And then on top of the floating room, our granite, our optical table, also have like second stage of vibration damping system to reduce the vibration. So we have the system, then how do we make a sample? Basically, our day is really like 90% of the time is really just trying to make a sample. And the reason for that is because to get in those 2D materials to build our devices, actually very time consuming. So, you know, we take graphite flake and we try to copy it using a tape, making it as thin as possible. And this is a boron nitride. It looks transparent because it's an insulator. And we use this kind of tape and stamping down to a silicon oxide chip. And then accidentally, some of the flake will be deposited onto the chip. And then you are using the microscope to try to find in those flake, you know, because you are using tape, so you have a lot of glue. So sometimes you can find a good flake, but that flake will be like very often will be contaminated by those glue. So for example, this is a graphene, monolayer graphene. We find it and we thought, oh, finally you can build a device. But when you're using the FM to check in the surface, you find that there's actually a lot of dirt on top of it. And basically this is a trash. So we need to find another graphene. So it's involved a lot of, it's very time consuming. And then with that kind of material, we can try to build our sample. This is our transfer stage. We using a glass slide and then having a piece of PDMS. It's pretty soft, so you can kind of like stamping down and raising up without crashing your silicon oxide or your glass slide. It deforms very well with the surface. And so you can put thin layer of polymer. You can think of it like a glue. When you heat it up, you can grab in your material. So you can pick up a few nanometer hexagonal boron nitride. And using that boron nitride, you can pick up the graphene. And then the amazing part is that you can only pick up part of the graphene and then rotating an angle and then stamping down to pick up the second part of the graphene and making a very precise twist angle and then getting the Moiré pattern we want. And then having this stack of 2D material, we can flipping it and then deposit it onto our device, and we can have some metal contact to contacting with our graphene, and then we can send it into the microscope. So for example, this is some picture I take when I'm making a device. You see this kind of thing is the polymer. When you are getting close to your surface, you will get some interference pattern. I think it's called some Newton ring or something. When your two film are very close together, the light will interfere and give you color. And because when you're stamping down, you have this kind of angle. So this part has already made a contact to the surface, so you give you a yellow color, but here has a tiny little distance. So it give you some color, and the color will tell you how far your polymer is away from the silicon oxide. And you can basically using this way to picking up a boron nitride, for example. And here you can see that on the line there's a graphene, and we can pick up part of the graphene. And then when you pick up, you can tear the graphene. So you see there's actually a cut here. So by you doing so, we can using our boron nitride, pick up part of the graphene, and then we can later rotate our stage and pick up another part of the graphene. So, and well, this is, well, as I say, like doing snowboarding, it's really like, you fail a lot, and then you only learn when you fail. And sometimes when you fail, you already spend like 2 or 3 hours, and then all the time just go into waste. And that's just including the transfer process. It doesn't involve that kind of flake collecting process, which would take even more time. So yeah, it's really sometimes very, very frustrating when making a failure. But this is a successful device that I eventually make and deposit onto a gold pattern. So we can install it into a microscope and then take a look at it. So you would think, yeah, finally we get the data, but unfortunately, a lot of time what we get is a wrong angle and then some dirty sample. You see this is a Moiré pattern, and the atom is much smaller. But yeah, for example, this sample is had a lot of dirt, maybe coming from the polymer. So we have to, like, make another sample. So yeah, so this is a brief introduction about how to make samples. So yeah, I don't have too much time, so I guess I will just introduce about the metric angle twisted bilayer graphene that I been involved like 2 years ago. So I already show you that twisted bilayer graphene is by twisting 2 Dirac cone, it's like hybridizing 2 Dirac cone. And then when the angle is right, you get 2 flat band. And this is a simulation from MIT group. When you twist in the angle, you can basically doing the band folding and creating a flat band. And when the flat band, what flat band do is making the electron very close to each other, and it interact more strongly and create more interaction effect. So this is one of the device that gives some good data, and you can see there's a Moiré pattern. From this angle, from this distance, we can calculate the angle, and this is a density of state. And compare with the theoretical calculation, we see that this two sharp peak is exactly the flat band shown here. And this is a spectrum taking a lot of different gate voltage. in this axis is a density of state. For example, each line here, and at different y-axis is in different gate voltage, and we plotted the intensity as different colors, so it can better visualize in the evolution of the band structure. And so you can see when your flat band is far away from the Fermi level, they are like two independent flat band. However, when you get close to the Fermi level, you see that it has a sudden change. And when we are doping the band structure, it shouldn't change the size if there's no interaction effect. So it should just be a constant shift because we are changing the Fermi level only. However, you see when these two flat bands getting close to the Fermi level, it suddenly changed the shape. Even the intensity has been changed like dramatically. And you can see at here, the band has even split into two. And this is the indication of some strongly correlation effect. And we can using some theoretical modeling to simulate the effect. And we confirm that in this device, we do have a strongly correlation effect. So yeah, I guess later I was planning to introduce another 2D material that I involved like last year is twist double bilayer graphene, but I guess I don't have too much time. But the moral is that it's very similar, but instead it's stacking two Bernal stack bilayer graphene. Bernal stack is the nature configuration of the graphene. So basically, when you get a bilayer graphene, when you scratch graphene, you get monolayer, you get bilayer, you get trilayer. And this is a bilayer graphene. And if you're stacking them, you also have some strongly correlation effect. And for example, you can see the band structure can be changed because you have some electrical field. And at the hot filling, we also see some correlation effect. And when we add a magnetic field, we even see some splitting in the flat band. So yeah, this is a very interesting material platform. So when you twist different thing, you can see a lot of different effects. So that's why there's a lot of like paper coming up like recently. So yeah, I guess I will stop here, and if you have any question, I'm welcome. I'm willing to answer some of them. So yeah, thank you.
Thanks so much, Cheng-Li. Maybe first we can unmute ourselves first, and then let's give it up for Cheng-Li first. Thank you so much.
Oh, thank you.
Okay. So maybe I can first ask one question. So here there are lots of like twist systems, right?
Yeah.
So how to like intuitively say which one is interested in or why they are interested? I mean.
Oh, so yeah. Somehow you can think of it on the application way. So to save the human, save the world from like climate change, we want to find a superconductor because it can save in the energy. You can like half of the energy, half of the electricity got from the power plant is lost due to the thermal loss, due to the like resistance of the wire, of the cables. And if you got those kind of power transmission line into superconductor, you can save in all the energy. So yeah, so superconductivity is like something people are very excited about. And in twisted bilayer graphene and twisted trilayer graphene, they see some superconductivity. And so that's very interesting. And topological effects also something people are interested about. And actually, most of the graphene system have some topological behavior. And if you control the topological material, you can get in some edge state, and then people are thinking using this kind of edge state to doing some quantum computing or some different kind of things. So those are also very interesting things. But I think basically investigating all the behavior is like fundamental research is also very interesting. But yeah, I mean, making a graphene, graphene it's not a topological material, but when you're stacking them, you can making it a topological material is also like something very fascinating. So yeah, I think they are all very interesting. So.
Yeah, thanks. Other people, please. Yeah, go ahead.
Can you remind me again, please, how to put the graphene in the, put the twisted bilayer graphene in the superconducting state? What are the requirements?
So actually, people doesn't really know the mechanism of the superconductivity in twisted bilayer graphene.
So
yeah,
you tune the carrier density, and at some point you will become superconducting.
Yeah, and people find it's close to half-filling insulating state.
And the bottom gate is sufficient to do that?
Yeah. So amazing part of this kind of material is that you usually get a large in a Moiré pattern. So usually it's like 10 nanometer, around 10 nanometer. So so if you fill in, so the 10 nanometer meaning that you can use that to calculate the carrier density, how many carrier density to fill one electron into like a 10 nanometer by 10 nanometer Moiré. That's actually matching the capability of like silicon oxide or boron nitride, that kind of material. So yeah, it's happened to be sufficient and yeah, very like kind of a coincidence.
So in your experience, what are the backgate voltage? For example, 17 volt or like 7 volt?
So for twisted bilayer graphene, usually 40 volt so silicon oxide wafer we are using is about 285 nanometer thick. In that case, usually 40 volt is sufficient to fulfill the system. And this plot is a little bit complicated because there's some tip effect. So it's making things complicated, but usually 40 volt plus minus 40 volt is sufficient. And usually the silicon oxide can survive up to 100 volts. So it's more than enough to study this kind of material.
I see. Thank you. In that, because you mentioned that you're calculating actually based on the size of the cell of the Moiré pattern. Does that mean that the larger Moiré pattern require larger voltage, or it doesn't really work like that?
Larger Moiré cell, meaning that to fill one electron into each Moiré unit cell, it becomes easier because when you're gating it, you get, for example, 1 volt will give you a certain amount of electron into like 1 centimeter square area. So that means if you get a larger Moiré cell, it becomes easier to put 1 electron into that unit cell. If your unit cells shrink to a very small area, then to put 1 electron into each Moiré cell, then you have to put a lot of electron into like a unit area. So that would be harder to gate. So you actually want some material that has a large Moiré unit cell to study. Otherwise, the silicon gate will not be enough. Yeah.
And one last question is, you mentioned you've seen some like bubbles when you are putting graphenes together, the defects, right?
You mean like this kind of stuff?
Yeah. So in those like things, did you try some kind of like, previously which that's not what I did here, but back when I was in academic Sinica, Taiwan, we tried to do some like hydrogen annealing. Have you tried that?
Yeah, we try all kinds of things. And it's still very hard because some material, some like dirt, it just doesn't want to move away. So we try all kinds of things, all kinds of solvent, hydrogen, argon, and sometimes you use an FM to try to move in this kind of thing away, but it's still inconsistent to make clean sample, and it's still something we are working on.
Okay, it's dark magic. I'm just curious because we use hydrogen annealing, but in terms of bilayer graphene, no, I mean twisted bilayer graphene, I'm not sure if the heat will actually thermalize the graphene such that you have previously, maybe you already aligned very well, and after the heat, it might just go back, relaxed back to the natural state of bilayer. Just curious.
Yeah, it's totally possible. And yeah, so it's very hard.
Cool. Thank you.
Can I ask a follow-up? So do all other transport people, I believe they don't take a look at the samples like you did here, right? I mean, this is like, because you're doing SDM, so you can see the surface of the sample, you can know the true quality of the sample. So for those people who you're just doing transport or other measurement, do you think they know their sample quality as good as you do, and do you have any concern with their data?
So we don't do transport, but the thing that's different between STM and transport is that because STM need to using a tip to probe in the surface of the sample, so you can't have anything cover your sample. You have to expose your graphene. So when you are making a sample, when you pick it up, because you cannot protect in your sample using, say, another layer of HBM. So your graphene must touch some polymer, and that's the reason why it becomes dirty. But for transport experiment, they don't need to put a tip on top of the sample. So when they are making it for a sample, they can pick him out graphene, tear it, and then picking out another HBM. And basically you can protect in your graphene between two HBM, and then it will become very clean because it will never touch the PDMS or never touch the polymer you are using. It only touches silicon oxide. And silicon oxide is usually very clean. So for transport people, the device is usually much cleaner, but it's also hard for them to know whether it's actually clean or not. But I guess it's clean because they never touch the polymer. And most of the dirt we get from is more like a polymer thing. Sometimes they are insulating, so you don't see them, but your tip just, you feel something strange. So yeah.
I see. So next question. So how, like, okay, so you put your 3C bilayer graphene on boron nitride, right? And you also say some people also put another boron nitride on top of their 3C bilayer graphene or graphene, stuff like that. So so how do we know this boron nitride will not affect like the 3C bilayer graphene, or the angle between boron nitride and graphene? Is there any like how do we know that boron nitride will not affect the
Yeah, it's a good question. So let me see. In the very beginning, like when people just started to do the experiment, in the beginning they put it on silicon oxide. Silicon oxide is clean, but it's actually not electronically clean. There are a lot of impurity buried inside the silicon oxide. So you will have a lot of local doping and making your sample behave like poorly. So people are thinking about how to get rid of the silicon oxide, making the sample more pristine. So one way the people first think of is suspending the graphene, basically doing some fabrication and making your graphene suspended in the air. However, that's also not good enough because it's making it become very far away from the gate. So it's become harder to gate. So people are trying to find a good substrate that is clean and not interacting to the graphene, and HBM turns out to be a good candidate because it's also 2D, but it's a very large bandgap insulator. It has, I don't know, 2 volt or 4 volt. It's so big that it will almost never interact with the graphene. The only way that it affecting is that it creates a Moiré pattern, and it will create some effect to the graphene. And for example, it can create this kind of starter butterfly, and it can also create some, graphene have have two lattice have two bias, have two atom in a one unit cell. It will create a slightly different potential in that two atom, and then we call it like AB sublattice splitting. But otherwise, boron nitride almost didn't interact with the graphene. So yeah, unless you align your BN with graphene, otherwise BN is almost invisible in most of the cases.
Okay, so basically just be careful this alignment between boron nitride and the graphene in between.
Yeah, but sometimes you won't align them to get more fixes. So
oh, okay, got you. Okay, thanks.
yeah.
How do you actually align them though?
So when you scratch the flake, for example, so you know when you try to cleave a crystal, it tend to cleave on some nature direction. So if you look at the flake, a lot of time they have like straight edge, and those straight edge, if you measure it, it has some like 120 degree or 60 degree. So you know that that edge is just the like A axis or B axis, that kind of thing. So you can just visually identify the edge to determine the crystal orientation. Or if you really want to be precise, you can do some like second harmonic, that kind of like some optical way to detecting the crystal orientation. But a lot of time, you just make a lot of samples, and then some of them will align.
Oh, okay.
So yeah, it's a very time-consuming experiment.
Any other?
I have one more question. So has anyone tried to do microwave measurements with the superconducting twisted bilayer graphene, or just DC measurements?
Microwave, let me think. I'm
Like,
not aware of, yeah, for example, like MIM, that kind of thing. I'm not aware of that. Yeah, I'm not aware of any. Do you expect in any different at high frequency?
I don't know. I'm just curious
Okay, yeah.
to know if superconducting graphene follows like Mattis-Bardeen behavior, or other how the impedance compares to other superconductors.
Oh, I see. Yeah, that would be interesting. But because sample is usually small and there's some angle, there will be strand, so your angle can be different at different area. So unless you can shrink your bin size to very small, otherwise a lot of time you will just get a lot of blurring effect from the angle in homogeneity. So that would be a very challenging experiment, I think. And also, I'm aware that some people were using like microwave impedance to measure, for example, tungsten ditelluride, the edge of tungsten ditelluride, and you can see the edge conduction channel. So maybe you can use in that technique to detecting the topological behavior of twisted bilayer graphene. But for superconductivity, yeah, I think it might be pretty hard because the superconducting temperature is usually like 1 Kelvin, 2 Kelvin. So if you accidentally use microwave to heat up the sample, it will like destroy the experiment as well. So it might be challenging, but it's definitely an interesting experiment to do.
Got it. Thank you.
It's a follow-up question. Is there any like demonstration of Josephson effect? Like work it as a Josephson junction?
So recently there's a like a paper from also MIT. They are trying to make in like a Josephson junction. And yeah, let me try to recall that. Did they see AC or DC Josephson effect? I know they try to make a tunneling. Yeah, I think they do see the Josephson effect, but I have to track the paper.
From Pablo's group, the jury.
Yeah. It's Daniel. I think it's published on Nanotech, but yeah, I need to try the paper.
Cool.
Yeah.
Because we have a group here, led by Professor Eva Andri. Her group is also working on this twisted bilayer.
Yeah. She has a lot of good paper.
Okay, any question? Maybe I ask the final question. So like, what's the future direction, or what do you see in this field? Like in maybe 3 years, or 5 years, the field direction. What do you think?
Yeah. Well, so far, the nature of the superconductivity in like twisted bilayer graphene is still unknown. People are debating whether it's S wave or P wave, or like what does the superconductivity is coming from. Like even though the superconductivity temperature is pretty low, but if you consider in the carrier density in this system, it's fairly high actually. And in BCS theory, the superconductivity transition temperature is proportional to the density of state. So at such low density, this kind of transition temperature is already like comparable to the high TC material. So the superconductivity is definitely non-trivial, and by solving this is definitely one of the target. And I think this is one of the main target people were trying to do, and then maybe be creative by making different type of twists and different type of material, like combining different material. So not just graphene, you can make in some of the TMD or some magnetic material to, it's like a building some Lego. You have different material, you just stacking them differently, you get new different fixes. So yeah, I think there's a lot of things to do in the future.
Okay, good. Sounds interesting. So then thank you so much, Cheng-Li, and then so we will welcome. Thank you so much for coming, and hopefully you can really come to Rutgers. I mean, just have an hour drive, right? So hopefully we can meet you in person. So, and thank you so much for coming, all for coming. So I'll see you next week, and yeah, have a good day, have a good night. Bye bye.